Hello, Marcos. Hello, people.
Hello, people.
Hello.
Hope you're doing well. We are on room two, so we'll better start with our first presentation right away. If everyone is ready, we're gonna give them a couple of minutes, maybe. So, what's about the first presentation? Well, Ali are part of a team of librarians at the Center of Astrophysics, actually. They're passionate about public science education. You can call them as they. And they will be talking about Metasat, which is open, collaboratively developed metadata tools to support the future space exploration. And they got the mic.
Thank you so much. Should I wait a minute to get right to 8:10? I can start. Okay, I'm gonna wait the 30 seconds until we're actually at 8:10, just in case. Thank you. Well, gotta get myself in the middle of this. Okay. All right, everyone. Good morning. It's morning for me anyway. I know it's not for everyone, but good morning from Massachusetts. I'm Allie. I'm going to be talking to you guys today about Metasat, which is our project for making metadata for small satellite missions. This was introduced at OSCW last year, but I'm going to be giving you guys a little bit of an update to let you guys know what we've done for the past year. Before we do that, though, I want to kind of introduce myself, introduce who we are and why we're working on this. So I'm part of a group of librarians at the Center for Astrophysics here at Cambridge, Massachusetts. We work for the Woolbach Library, which serves the CFA, and we're the largest astrophysics research library in the world. So part of our mission as a library is to anticipate the challenges that impact the astrophysics community, both at the CFA and as a whole, I think. What this means is that we need to stay on top of trends not only in libraries, but also in astrophysics. And really where those two things overlap, in my opinion, is in helping kind of the scientists at the CFA work with better communication and collaboration. Because we know that there are a lot of teams at the CFA, there are a lot of teams in general in satellite missions that work with other people all over the world, right? We have teams here at the CFA who are working with some of the NASA labs in California, with the Naval Research Lab in Bethesda, with other people all over the world. So we want to kind of help them be able to communicate effectively. And we know that there have been a lot of issues with people when they're only able to kind of talk to each other remotely. I think that we've all seen that recently, since we're all kind of working remotely with each other more than ever now. But we do know that we often see some difficulties. So one example here is that there was a student team at New Mexico State University that was working on a CubeSat called Inca with some of the scientists at NASA Goddard. The scientists at NASA were building a part for the team at NMSU. But when the students in New Mexico got the part, they found that it was actually a millimeter too big in every direction and did not fit in their CubeSat, right? So they had to send it back and have it completely remade, and that costs a lot of time, it costs a lot of money. They almost missed their launch. They're very lucky that they didn't. And so just a tiny little miscommunication like that can kind of cause this ripple effect. We all know that if we've worked on satellites, right? There are some issues that we can anticipate that we know happen a lot. So for example, when we have teams in the United States working with teams elsewhere, we might have people using different units because the United States will not use metric. We spell things differently. You might have different terms and variable names for the same things. I mean, I have tutored students in physics before, and I have to tell them, you need to tell me what that variable is because I might have learned something completely different, right? And these aren't kind of trivial issues. These can cause really big problems. So one of the more famous examples is that in the 90s, NASA launched the Mars Climate Orbiter. They were working on this satellite with Lockheed Martin, and Lockheed Martin had written software for the satellite that used metric units like Newton seconds. But NASA's software on Earth was using imperial units, so pounds for seconds. The satellite didn't know that. It didn't have any way to convert between the two. And so what happened is when they tried to establish orbit around Mars, it ended up crashing into the planet because it was given the wrong measurements. So this isn't trivial. These are kind of these can cause really big problems that cost a lot of time, that cost a lot of money, and they weren't able to get the data out of that they wanted to. So what we want to do is we want to at least do our small part in making sure that these kind of mistakes don't happen, or at least they happen less often, right? So that's where we come in. We're working on Metasat, which is our linked data vocabulary of satellite terms. We're trying to make a list of linked data URIs that cover kind of all parts of the satellite mission. We have information about the mission and people, so who's putting the satellite up and why, the launch, when did it get into space and from where. Ground stations, the data, how are we talking to the satellite and what are we pulling down from it? The hardware, the software, what is the satellite made of? What are maybe some off-the-shelf parts that we could use if we're making a satellite later? Because this is a linked data vocabulary, it can be used with any other linked data vocabulary like schema.org, and this makes it really flexible and extensible. And if you're not familiar with linked data, the W3C describes this as a collection of interrelated data sets on the web. What this does is it kind of makes data a little bit easier for machines to access, and as well as for data sets to kind of talk to each other, if that makes sense. So over the past year, we kind of had a few big things that we've done. So we have kind of three major parts of Metasat that we've worked on. We have our vocabulary of concepts. I wrote here that we have about 1,000 concepts. It's more like 1,500 that relate, again, to all parts of the satellite mission. These aren't hierarchical. You can use them in any relationship that you want. We do have them grouped on our website by segments, so like launch segment, space segment, ground segment, as well as different concept types, and I'll give you some examples of those in a little bit. We also have a set of metadata crosswalks. These are tools that we can use to kind of match concepts between vocabularies. So if there are other linked data vocabularies, dictionaries, we have multilingual dictionaries, for example, as well as other databases. We can link between our terms and terms that other people are using. And finally, we also have a collection of JSON-LD example files. You can use linked data in a lot of different formats. We're recommending JSON-LD specifically because it's really easy to write, it's easy for machines to read, and it's very flexible. So what we've done is we have a set of files about real missions that are written in JSON-LD to kind of inspire you guys to see what you can do with Metasat. So here's an example of a file that we made for a mission called Picard. So you can see that this is set up a lot like plain JSON. We have our keys and our values, our key value pairs. What makes this special is this context section up at the top. You'll see that we have this line that the vocabulary is schema.space/metasat. That's where all of our terms live. And so what happens is that if you have something like mission, that gets expanded into schema.space/metasat/mission, which is our concept for that. And you can see that on this file, we have just like a lot of information about this, what this is. So we can see that this is a solar science mission named Picard that's coming out of France. We have information about when it was launched and from where. We have information about the spacecraft itself. We have its COSPAR ID over here. We have its NORAD ID. And more information as we keep going. So at the same time, this is just one example of how you can use Metasat and JSON-LD to describe this mission. There are other things that you can do. We try to be very flexible, and again, these are just to inspire you to what you could do. We also have our website is live. That's schema.space. We have all of our concepts living there. If you go to schema.space/metasat is where those are. And then after that is where the actual term lives. So here is an example of what these pages look like. So this is the page for FPGA, the Field Programmable Gate Array. At the top of each of these, we have the term itself. Underneath, we have the permanent URI to that term. Then we have a description. We always have a definition for what it is. Underneath, we have examples and synonyms. Not everything has an example or synonym, but some do. And we do have the website set up so that if you search for a synonym, but we use a different term, you should still be able to find it by the synonyms. And then down here at the bottom, we have the segments and families. So this one is part of both the space segment and the ground segment because your FPGA can be part of either your ground station or your satellite, as well as these families, which are kind of things that we put together by what we felt were similarities. So here it can be part of both communications and computer hardware. We have other ones as well, like orbital mechanics, mission data, all sorts of different things. Crucially, at the bottom of each of these pages, we also have this suggest and edit button. We really do value everyone's feedback. If there's any way that you would change any of these, you can always click on this. Right now it's a mail to link. It might become a form in the future, but we always look forward to your feedback to us. The other thing that's on our website is that we have a resources tab up on the top that includes guides for people. So we're anticipating that people using Metasat will probably be familiar with satellites and space research, but they might not be as familiar with databases, metadata, RDF, that kind of thing, JSON LD. So we have a set of guides that we hope that you guys will find helpful. And finally, we have our first implementation of Metasat, which we're all very excited for. So yesterday at the SatNogs update, Freddie mentioned that Metasat is being used with the SatNogs API. So this is kind of what that looks like. This is a screenshot from the satellite list API, and you'll see up at the top, we have this context section that links to our Metasat vocabulary. So if you ask for the API specifically to give you JSON LD, that's what you'll see is it links to our Metasat concepts. There are also other people that we're working with too. So for example, we're working with Jonathan McDowell here at the CFA. You might be familiar with Jonathan's Space Report and GCAT, the General Catalog of Artificial Space Objects. He gets a lot of really good data about satellites, but it's all public, but it's kind of hard to use sometimes. You can get it as a text or a TSV file. So we worked with him to actually crosswalk his terms to Metasat. So we're hoping that we can make those a little bit more easily available by using it with Metasat. We also have a pending agreement with NASA. We want to work with them on their Small Spacecraft Systems Virtual Institute. They have a database called SPOON, Small Sat Parts on Orbit Now. We're hoping to, again, crosswalk their terms to Metasat to make it a little bit more easy to use. And we've also had interest expressed by other potential early adopters as well. The reason that this is important, that we want so many people using this, is that one of the potential applications in the future is that you could have a federated search, which is where you have one search application that pulls from a bunch of different databases. So you could potentially search for a satellite and you could get all of Jonathan McDowell's really detailed information, as well as the SatNogs information about the transmitters and the SPOON information about what kind of hardware is on it. So you get like a really complete picture of that satellite and what it's doing. A little bit about what our next steps are going to be. We have our official 1.0 release is going to be just around the corner, which we're all really excited about. We're also going to make an RDF implementation of Metasat. That might be jargon for you. What that really means is that will make it real linked data. It makes it easier for machines and APIs to use. And we're also incorporating into Wikidata, which we're really stoked about. So we have a Wikidata item for Metasat as well as a Wikidata property. What that means is that we can start putting Metasat terms into Wikidata. Once they're there, we can use them to describe satellites on Wikipedia, and that might make them more easily Googleable in the future. And finally, if you guys want to contribute, obviously this is all open and we're really looking forward to what we hear from different people in the satellite community. We do have a GitLab repository that you can always leave an issue on. You can email us. Our team is at metasat@schema.space. You can email me directly if there's anything in this presentation that you find interesting. In addition to giving us suggestions, you can also always ask for clarifications. Let us know what kind of topics are unclear because we are writing guides that we hope will help you guys. So with that, thank you, and I am excited to take your questions.
Awesome. Please, people, don't hesitate to come over and ask your questions. You can also use chat, or you can use our Matrix channels.
How, okay.
Will I upload my slides? I do want to upload my slides. If someone would help me do that, I would love it.
Yeah, we will. We will upload them.
Okay.
I'll look over it.
I got one question. So, as a guy working on the Polaris project, so the machine learning analysis for spacecraft, so we have a great deal of use for metadata, because we would like to learn what the temperature is reacting to, and then we want to see on other spacecraft if other temperature sensors are reacting the same. But for that, we need some kind of a federated search, like to be able to go to other spacecraft and take those temperatures, and just by semantics, like we want temperature parameters. That's what that's how we want to search. For that to happen, do you have missions that are already using Metasat? How do you see that multiplying? People onboarding with metadata schemas.
We don't, as far as I know, have any particular missions that are using Metasat yet. Right now, the scope of Metasat is more to describe the satellite mission kind of as a whole, so what the satellite is and what it's doing. Having it actually have metadata for the data itself is definitely kind of a future, something that we want to, have in the future more.
Okay, then we might come in and contribute for that then. Okay.
Yeah.
Cool. Thanks.
Awesome. I actually do have a question. Well, as far as I understand, space technologies are changing in a very fast pace. And does Metasat have that into mind when it was designed? So in order to be future-proof, if you like?
Yeah, so Metasat is very extensible. Right now, the way that it works is all of our terms they have permanent URIs, right? And we know that those terms might change in the future, or they might have technologies that exist in the future that don't exist right now, for example. We will never delete any of our URIs. We might deprecate them, if that makes sense. So any update to Metasat should not break any applications that you make. But we are working on one of the things that we want to have ready with our 1.0 release is kind of a versioning schedule, so that we can kind of regularly make sure to solicit feedback from the satellite community, figure out what do you guys need, what are we missing, what can we add, what can be deprecated. So we're hoping that it will continue to change and evolve as the field does, yes.
Awesome. Also, for those that don't read the chat, Dana from the Metasat team has said that they are just getting started with specific missions adapting, and they're still developing tooling to make it easier for individual missions. So we look up to that too. Awesome. That was really cool. Any other questions? Let me see. I don't think there are any other. So people stick around, and we're gonna go to the next presentation.
Thank you so much.
Thanks. That was really interesting.
Thank you.
Thanks a lot, Ali. Go, Metasat, go.
So next presentation, Bo is a research engineer at ISA Superhero, and he's working on space-related software, ground segments, and CubeSats, and he's gonna talk about nanospace, an open source tool to help concurrent engineering teaming in CubeSat preliminary design. Well, actually, it's high time we forget, people forget using Excel and start using database like we should always do. So wait a bit to upload that. Will take some time.
Okay, thanks. Thanks a lot for the introduction, actually.
Thanks a lot for speaking.
If I can share my screen, I can just share it if you want.
Just wait a second, Manthos, to upload your presentation. Maybe it will take a while. Was that a big?
Sorry again?
Was it a big file?
I didn't really pay attention.
have,
8 megas.
Right, speaking, Thibaut, do you have videos in the file? No, or
No. Just
okay, it should be all right then.
I do that on purpose.
Just 11 megabytes. Just give some time to the server to transform that into BBB
Okay.
readable format.
Okay.
70%.
Okay.
It's a
So
slow
well,
process.
I can begin with the introduction actually, even with no slides. Next time I take a board here and I will explain it. So hi everybody. So I'm Thibaut Gatto. All this work has been all the technical part actually was done by Lucien Sénanoche. You will see his name on the first slide, and we work together on this. On that, actually, it's a European project we are on. It's called NanoStar. The goal, it's a challenge. We are building, actually, we are proposing challenges for students from different institutes. And the goal of the project was, like not all the goals, but one of the goals was to develop one software tool suite. Oh, thank you. Perfect. And can I change slides?
Wait a sec, so Manthos will give you
Okay.
presenter rights. I can do that by myself.
Oh, wonderful. Thank you. So one of the goals of the project was to build tools, software tools, to allow students to do preliminary design of satellites. So preliminary design, it's phase 0, phase A, sorry, in the ESA definitions. It's globally, it's how you do the precising of your satellite. I guess you all know that. You are giving more or less is giving the subsystem budgets, like what's the final mass, final cost, and so on you are expecting for your satellite, and you need a lot of communication. And I'm glad that you insist on it in the Metasat presentation, actually. Oh, sorry, I have to find the way to do that. So when I was talking first about, when I thought about preliminary design, I was more thinking on you have a nice interface with a nice ergonomic interface. You can build your little piece of the nano satellite, putting them together and do some simulation for it. And when I discovered reality, it was more like you have big spreadsheets everywhere. And even if you put colors on these spreadsheets and little pictures someone, it's still a spreadsheet. But okay, at least to do preliminary design, we have a lot of tools, like a lot of software tools that are, part of them are open source, but not all. And that's a big issue in our case, because we wanted to, in NanoStar, we explicitly wanted to do all the thing open source. It's for education, it's for students, and for human knowledge. So it's very logical to have something open source, fully open source. And we have many things there. We have different, we have libraries, we have independent tools, and we have also methodology. I will not go very deep in that. I prefer to speak about methodology. So the new trendy way to do preliminary design is concurrent design engineering. I'm sure also you are all familiar with that. The concept is more like is how to make experts talk together and be very efficient in the preliminary design process. So with some interaction, but together in the same room. For NanoStar, we wanted to make concurrent design engineering, but in separate places, like the pandemic, the COVID pandemic was a very good example. Actually, it was totally unexpected, but we build tools for that. So we have students in teams to do preliminary design in different institutions. They are forming. They are in the same team, but in different institutions. We have 5 institutions working on that. And we have chosen some, like, we want to make something open source, and we have chosen to rely on databases better than spreadsheet. I will not extend on that, but that was, for us, it was a key point for doing like efficient work on that. So we propose the first year we propose a full suite of different software to do all the systems descriptions. And we were with IST, with the Técnico de Lisboa, Isaías Supero, we are still responsible of the consistency of all of that. But as you can see, it's a big mess, and I'm going just to focus on the backbone of this suite is what we call nanospace. All of that to introduce nanospace. Well, so nanospace, just a little demo style thing. You can access it. Actually, there is a test server running. You can access it directly with this link. It's you have some documentation associated. You have a GitLab. We entered the 21st century, so now we have a GitLab, and we can publicly, like, it's easier for us to publish our code. Actually, it's all of open source, of course. So the interface, what is the thing of this nanospace interface? We wanted to have like a spreadsheet-like model, but with the databases behind, for many reasons. I will go further on that. So what's basically what we have when we go on this interface? We have a project tree with the different subsystems. We can put, like, it's totally, you can manage it the way you want. You have a project tree. You have some mods for your satellite. For example, when you are in a survival mode, you have not the same consumption as in the nominal mode, for example. You can visualize the data and add data in your database through this interface. It's very, very simple, no issue. But what's interesting, most interesting, the data we are using, we wanted to keep close to a spreadsheet style edition. So you can, for example, you can do some little calculus in the cells. You can have dependency between cells of this interface. But you can also, like, for example, change units, do little math. We are using MX parser behind, and it's very, very simple and very, like, efficient for our needs. And also, you can share the project with other users. That's the goal, the final goal of the thing. You can share it, so you can have many users editing it. But that's not the most interesting, like, that's just what you can see here. What's interesting is what's behind. So behind the technical choice and why we have done that. So we wanted for our students to have something that was platform independent, so they can just connect with the browser to something that allows them to share the data. Why not using, for example, like a Google Drive thing like that? For many different reasons, we didn't want to use that. I guess you would know. We want to use the REST API to ease a third-party connection for when you are, for example, if I'm dealing with Polyastro script, I want to keep my script and easily upload them, like upload the result in the databases, like, automatically. It was one of our requirements for that. And at the end, we wanted ACID property for the database because we have concurrent access on it, and we need something robust about that. So we choose, maybe it's not the best choice. I agree. We are not expert on that. So we choose a Neo4j graph database for doing that. Neo4j has ACID properties. And for the front end and back end, we use Angular and Spring Boot more for practical reasons than real deep technical reasons. It was more we were comfortable with that. So So we have a front end, we have a back end with the databases on the architecture. But more interesting, what's the link? The link with third-party application. For example, you are using some scripts in Python. How you are going to connect? So we are providing a REST interface. You can directly connect to the REST interface with your application. But sometimes users don't like it. Yes. Okay, thanks. Sorry. You want to use, for example, directly your Python script to do that. So in Python, we have written a little interface, a little API actually, to do the connection with the REST interface. If you don't like to work with REST interface, it's your right. And you have like 3 lines of Python code to connect to that, like connecting to the database, and after like uploading data from there or downloading data from there. The same thing we have done with Angular, with Node.js. We have written a little component. It's public. It's on the NPM repository. It's literally 3 lines of code to add some elements in your web application. For example, I have done that for my students. It's just it's a link budget calculation, very easy thing. You put the altitude, and according to our some default parameters, you click on the button and you get the synthesis of your link budget you want. And what we do with Nanospace, we add 2 little things, 2 little components, like to ease the upload and download, to update the databases and retrieve the elements. You will see here, it's not fully automatic. It's it's a manual. You are doing that in a manual way. But the idea behind is, of course, you can use the access automatically in your scripts if you need to. For that, we are working also, it's not done yet, on the final architecture we are targeting is to implement a message broker that allow to send an event on an event bus to warn the applications that are updating when the database is updated. For example, if the altitude changes, you want to change everything. So what I want you to take home with this presentation is we were looking for a way to integrate very easily third-party applications to some centralized databases for our preliminary design. We want to deal with concurrent access, remote located team context. So in the pandemic era, it's quite trendy actually. The code is available, open source. You have I put the 2 address. I apologize, it's not totally stable, and we are still in the debugging process, but you can try it. We have a Dockerized version. If you want to install it on your own server, it's possible. It's a web service, so it's not that easy to go through the process of installing all the Angular dependency and all of that. But you have the Dockerized version if you want to try, and it's working. It's working. So what we want to do in the future, it's more to deal with the event management. We have a very after your talks that comfort me in what you were thinking on the formal pipeline management for the different, if some you want some data are impacting some result in your preliminary design. We don't have something very formal to describe that, and we are thinking on the model-based engineering system designing for doing that. And so what you have said in the doc presentation, the doc presentation, Boris, for example, is very meaningful for us. And we want also to check the resilience of our method to work for preliminary design using existing stuff like docs or GMAT, for example. That's also, if you have a question, I would be glad to answer it. Thanks for your attention.
So people, there is a question from Boris. Thanks, Thibault. You can count. He says that you can count on Boris Agré's support. Boris Agré from the Observatoire de Paris. And you'll be given a nice docs logo too. So yeah, there are other questions. I would be more than happy to facilitate them and also ask one of my own. So, first of all, kudos for using AGPL licensing. That's really cool. That's the way it should be. And furthermore, are there other concurrent design engineering solutions that are web-based and could facilitate your needs? Or if there are, how come you didn't choose them?
Yes, good, good questions actually. For the AGPL, it's just we wanted to have a contaminated license such as a GPL, and the only one we found that the industry cannot just take us back and use to deploy their own server on for web application was Affero GPL. It's more like we don't want people to deploy our solution and make pay for that. It's we want to keep it for education. It's important for us, and I guess your the OSCW community will agree on that.
Yeah, it's also useful for the whole community, and I think that choosing a very viable license like AGPL can be effective on that. Also, kudos from Konstantinos Kanavouras. He likes the tool and would love to try it. He's from the ASA team. Boris?
Yes, can I ask a question? Thibault, what's your plan to make that testable and available? Because I went to the website you indicated. At the moment it's yes, private, and it's completely understandable. But what's your plan?
Maybe I try sorry for that. I try my best. It's pretty it's not very common at ISAE to release some open source and things like that. I'm still on the process. Normally you should have an access. The GitLab we are serving should be public. If it's not the case, let me know. So you should have a full access on the code of all the code basically. If it's really problematic to access the code through the ISAE server, I will put it on GitLab and or somebody will put it on GitLab to avoid any legal issues for the community. Normally, now when I'm testing it, it's public. So if you have trouble to access it, just let me know.
There was another website you indicated, something like DCA-nanospace, yes. and that's also closed. Well, another one, another link in your slides, talking about the front end.
Yes, this one, I guess. This one should be public. It's on our test server. The second one I put in the chat.
That's the one I tested, and I don't know what you expect. If you expect us to see something there, not.
It's not. You have to go through a little. I hesitate honestly for this presentation. I hesitate to do a tutorial better. But you have. I can provide you the three elements to. You have to register to put a name. It's it's very simple on the top right of the website. I cannot share my screen, but it's the idea. You go, you register, and from there you can create your own project or import already existing project. We have some skeleton example in the GitLab I put in the chat, and you have a little documentation in the GitLab page. So I hope it's enough. If it's not the case, just mail me or say that to me. I will arrange it. I promise.
Everybody can start creating a project with this link.
Yes,
should be okay. Great.
Yes. With the test, it's a test server, so we regularly we update it, and we just crash all the database. So you have to you can make your own save of your own project. So it's quite a lot.
Website.
We don't give a guarantee for your work. If you work on it, for the moment we are trying and failing a lot, so it's ongoing work. But I will be glad to talk later with you about docs on how we can make the things together like for real.
Awesome. So I guess there are no other questions. Either in YouTube or in the Matrix public room. So thanks a lot. I will be checking it out too. Looks interesting. And I'm gonna call the next presenter, which will be Philip. He's an undergraduate student of cybernetic and robotics in the Czech Technical University in Prague. He's a summer trainee at the engineering department of the Vision Space Technologies. He will be presenting an open source onboard computer platform for CubeSats. And well, it's a newly developed family of robust and redundant PC104 format OBC modules and FlatSat. Let's check it out. Hi, Philippe.
Yeah, hello everyone. Thank you very much for joining my presentation. My name is Philip, and today I would like to show you an VST104 project.
Awesome.
I was working on this project during the summer of 2020 at the Vision Space Technologies company. I was under supervision of José Fajteriņa, that you may already know from the previous talks, and I was in touch with my professor from Czech Technical University, who is my bachelor thesis supervisor. He is Dr. Wojciech Petrucha. In this project, we aimed our focus on developing hardware boards dedicated for PC104 format. We developed a few onboard computer boards and also some testing and auxiliary boards. We can imagine the usage of this project in the future in mission control system testing and some development of FPGA algorithms. Throughout the project, we also try to contribute to the LibraCube initiative and also to support a local university club, TUTSAT, in the town of Darmstadt. The beginning, I would like to introduce you the VST family boards. We divided the family board into two main parts, the main goal boards and auxiliary boards. In the main goal, you can see board 0, Sierra, and Delta. Board 0 is just universal development board. It's kind of soldering array. It's nothing special. The next board is Sierra, which is a single redundant onboard computer. So you have a module with only one onboard computer. That's all. But in module Delta, you have two onboard computers, one of each side of the module, so you can independently switch between the modules. Element Foxtrot is actually a FlatSat adapter that is capable of hosting up to 4 modules with its own power module. So you can power it from something different and you don't need to use power module. And then there was a board Whiskey, which should be a radio adapter that wanna try to change it for a Wi-Fi module. But unfortunately, we placed this project on hold for now. I would like to introduce you some features of the onboard computers. You can see here there is a board Sierra and Delta. They share the same specifications. They are rated for actual flight because we are using components that are matching the military rated temperatures from -40 up to plus 125 degrees Celsius. And also all of the components are automotive qualified. So we match these two strong requirements for the flight mission. Unfortunately, we are not working with radiational hardened components because of terms of costs, but we try to implement this radiational hardened in kind of layout. Delta has double redundant onboard computers. That means you can switch in between of them. And also we are using memories in triple redundant configurations to deal with single large events. As you may notice, we try to shrink all the components to the smallest layout possible. And in this way, we are trying to maximize the payload sector. The payload sector is represented with this grid. The user can change it and place their own payload there. It's just kind of representation that nothing is actually placed there. Here you can see some OBC specification. This is the main header. You can see that we are using almost the whole PC104 header. We have plenty of interfaces such as CAN, bus, UART, SPR, I2U. We are using 22 general purpose user pins that you can modify. You can read analog, digital signals, anything you want. We also support some signal checking and maintenance signals such as CPU mode or synchronization or fault collector. So we have plenty of means how to communicate with the OBC and the rest of the satellites. Here are some specifications of the board Sierra. It's shared with the board Delta because they are the same OBC actually. We are using high-performance STM32 microcontroller. It should be the best in the family of these controllers. And we are capable of running up to 78 megahertz. We have two sources of external clocks, low speed and high speed, 32 kilohertz and 26 megahertz. We have external flash and FRAM, as I said before, in the triple redundant configuration. We have plenty of peripherals, and you are capable of debugging and programming the board using this small connector on the side. It supports SVI and UART programming and debugging. The board is full of interesting features, which I will be talking in the next slides. This is just for imagination. This is the schematics of the board, of the one onboard computer. Here are some pictures of the KiCad. We are using 6 layers, PCBs, 3 layers for signals, 2 layers as ground plates, and 1 layer for power delivery. And here are the interesting features dimensions. This is the picture of the board Sierra from the top, from the bottom. This hole is the one hole, yeah. So you can align it in your brains. That is the same board from 2 sides. In the middle is the huge MCU. Quite interesting part is this top area because it's plenty of small isolators. You can isolate your MCU from the main PC104 header, and you can do it by simply selecting which peripheral you want to isolate. So, for example, you can isolate only CAN bus or only UART on anything. You don't need to isolate everything. You can choose. We have a bunch of temperature sensors on board. They are marked with a green square. They are spread all around under the most important parts. You can notice the triple redundant memories. Here are some CAN bus drivers. This is the connector. It has the own ESD protection, so you can touch it without any damage. It's protected. And the last but not least, the important thing is the power management. We have kind of robust power management. Our board expects 3.3 and 5 volts as an input, and we are checking the lines separately for over voltage, under voltage, with protection in overcurrent. There are also integrated amplifiers that you can monitor the consumed current easily. If there is some fault on for example, on one line, let's say 3.3, it also automatically shuts down the 5 volt. So there are only 2 states: everything powered up or anything is running. And all these features should protect the board and make it safe to use in a space environment. I was doing the soldering by my hand. All the components are quite small. It was a bit tricky. You can see this is 1 euro cent coin, so you can imagine how the resistors are actually small. I just want to show you that you are actually able to assemble this board by hand. You don't need just some instruments like microscope and hot air, but it's not so special. And now let's move to board Delta. As I said before, it's an implementation of board Sierra in double redundant mode. You can see one Sierra is located here as a left onboard computer, and here is a mirror image of the one Sierra. So here's one onboard computer, here's the second one. They share the same layout, only with minor changes in tracing. That means you can use almost the same code for both of them, and also they share almost the same electrical characteristics. And you can see there is a huge payload area, and also the space under the VST logo is empty, so you can implement your own switching logic there, the logic that will be switching between the 2 computers. And the last board I would like to talk about is the Element Foxtrot. It's actually a flat sat board. It's capable of hosting up to 4 modules, so you can play 4 modules on it. It has its own power management, so you can power the modules from something different. You don't need to use the base CDU, so it's good for early stage of development, also for debugging, and maybe also for some presentations or some show-off of your projects in the future. This board also contains some nice features. You can power it from USB-C or external power adapter. You can choose between them through the switch. You can break the module if you don't want to use it through this breakable line. You can power it from your laboratory power supply using these banana jacks, or you can simply remove the temporary jumpers that are capable of hosting up to 6 amps. So it should be quite easy to operate in different ways. The board is full of fuses, so it should be quite safe to operate. We have integrated current sensing resistor. They are quite easy to probe. You can adjust the voltages using these trimmers. There is also USB-C handshaking integrated on the board, so you can connect USB-C smart charger from your laptop or smartphone, and the board should be aimed to negotiate the required voltage and current level with it. We have also over voltage protection, reverse polarity protection, so the input from external jack should be really safe. And if you want to use also the data from your USB-C, we have our own 5-volt USB data voltage conversion, and you can use this pinout to, for example, communicate from other modules with your charger if you are charging from laptop or something else. Our future work contains small tasks and some bigger tasks. I try to assume it in these 3 points. We would like to assemble and test more boards of the Delta. I hope we can manage it in the beginning of the next year. We would like to also add an external real-time clock to the board Sierra with independent power source, for example, some supercapacitor or small battery. And the last thing to work on is kind of redesigning the temperature monitoring for the board Delta, because right now it's running on the configuration that one onboard computer can measure the temperature of the other one, but not vice versa. So we would like to be able to measure the voltages in between the onboard computers. That's kind of a change. And yeah, so thank you very much for being interested in this presentation. Please free to check our GitHub. Everything is open source, and we'll be very pleased if you decide to contribute to this project. In that case, please contact Jose. You could use this email. So thank you very much once again.
Awesome.
Thank you.
I'm sure there are questions. I hope there are questions. I do have questions, actually. So, checking in channels. I was thinking, first and foremost, as far as I understand, all your hardware is under an open source hardware license. Isn't that right? Certain open source hardware license.
Oh,
right?
Everything is open source, so yeah.
Yeah. Secondly, so how come you decided on these particular pinouts? What was the?
Oh yeah. At the beginning of the project, we were considering multiple pinouts that we were able to find on the web, but unfortunately, there is nothing really synchronized. Everyone is using kind of their own pinout, so we try to squeeze the most we can together. And we are open for negotiations in the future. If this community decides to create one common pinout, we will be happy to implement it.
Okay. So first, Milenko in the chat says that it's CERN Open Hardware License version 2 strongly reciprocal. That's awesome. Congrats on that. Manfred asks, is radiation resistance a concern?
Oh, it's concerned not through the hardware parts, but it's concerned through the design. For example, the triple redundant memories and double redundant onboard computer. We may actually proceed with some readiness testing in the future through my university in Prague, but it's just an option. We are not sure about it right now, but we are thinking about it.
Any other testing?
Yeah, we are capable of running simple software on the board. All the elements should be working properly. And again, I would like to do more testing because I'm working on it on my bachelor thesis, so I need to do some measurements. But unfortunately, right now, my university is closed because of the COVID. So yeah, that's the problem right now.
Oh, no. I understand. That's really understandable. Usually that can be an issue when you're in a pandemic. Are there any available documentation? I haven't checked it out, to be honest.
Yeah, there is some documentation on a GitHub, but I am working on my bachelor thesis, as I mentioned, and this thesis should be the best documentation for this project.
Awesome. So when you will be finishing your thesis, we will be able to have more stuff to read and take a deep dive on.
Yeah, it should be really deep. Yeah, hopefully.
Great.
There is a question on the chat, Lefteri.
Yeah. Let me see. Which chat is that? Oh, which question, Manfos?
Here on chat here is Manfred asking if is radiation resistant a concern.
Yeah, as just a minute ago,
there's a question on the testing resistance.
Testing in the future, and that would be covered. Also, it was part of the. Are there something resistors part of a laptop current protection unit or something?
I'm not sure if you mean these resistors on the flat set, because there is nothing.
Maybe.
Kind of protection. These resistors are just for measuring. So you already know their value, and you can probe the voltage drop through these test points.
How come you ended up on a 6-layer PCB?
We're using only 6 layers for the onboard computers because we try to make the project as reachable as possible, also kind of low cost. And 6 layers is the last level of layers that you can actually order from some manufacturer for a reasonable amount of money. So that's the reason.
So in order to have that replicable and be truly open source, meaning that it's also people will be able to get one of these boards without paying a lot of money.
Yeah. I think the prices for one board here should be between 100 and 180 euros to order assemble. So it should not be that bad for an onboard computer, for a CubeSat.
Konstantinos asks, why is the second OBC in the Delta module flipped upside down?
Yeah, as you may notice from the picture, from these pictures, it was super hard to actually, this is one part of the onboard computer, this is the left one. And it was super hard to place the components and to wire them properly. And I would need to spend 1 more month to lay out the other onboard computer to the other side. So I just flip it, place it there, and then change only these traces on the top. So it was the approach of the minimal loss of time.
Yeah, that can be a good way to do stuff. Awesome.
Another question for me. You said about the price of the board populated. Have you ever tried to use, this is not about the project, but have you ever tried to use a service that populate PCBs, like to buy the PCB populated?
I'm not sure what you mean. We order the PCBs from China, from some manufacturer, in quantity of, 20 of them.
Yeah, but you order the PCBs, the boards only, not populated with components. So the price you said is only for the PCB, not for the components.
We are using some specific components, the specific devices, because they're all rated for the automotive, also temperature. So usually you need to pay a lot of money for the assemble house to actually put the wheels into their machines. So I think that's not really the way how to do it, unfortunately.
Yeah. Just asking because if you have something inside the info.
Awesome. Jan Mas, if I'm pronouncing correctly, asks, have you planned to subject VST 104 to an environment test?
Yeah, I plan it together with the other testing in my university. But for the COVID, it's quite hard to say. I think I need to do them because of my virtual thesis. So hopefully we'll be able to work on them.
Hi, I'm Jose.
Hey, Jose.
I just wanted to say that, we will at some point at least check out the prices to order it assembled. Also, we might even consider, one of the things that we've been thinking about is trying to do a mini Kickstarter, for example. Not necessarily on Kickstarter, but to have a way, like if you have 10 people buying the boards and you have boards, and then we see how much it costs. And if you already have these, then you say, okay, for this, I can make all of them already soldered. Because it was quite a lot of work, and Philip did very, very well. But it's not easy to find someone. It takes time to train the persons to the soldering, and it takes time to debug. And sometimes, if an error comes up, it's almost impossible to find out what broke the board, and then it just lost 100 euros.
Yeah. If you find a way, just populate it because it's an info that is needed inside the community.
I have a quick question from Olman Kiros Jimenez. Have these obviously been flown to any mission? Not till now, as far as I know, or plan to?
Oh yeah, we are in touch with a company from Romania. They are considering to use this board for their mission, but it's open topic. But there are plans, definitely.
Awesome. So thank you very much. Really interesting presentation and a lot of interesting questions.
Thank you.
See you around. So I'm gonna present the next talk, the next presenter. It's Mehmet Fatih. He's an astronautical engineer, graduated from University of Turkish Aeronautics in 2019. He's doing his master's in aeronautical and astronautical engineering in Istanbul Technical University. His main interests are on orbit determination, and he's developing an educational kit for high school about the physics, and he's also building a ground station, a radio RASAT, radio antenna satellite project. And he's the founder and team leader of the SatNOG stations on the UTAA. That was the University of Turkish Aeronautical Association. And yeah, he's working on a Doppler-based orbit determination with optimization. How you can determine the orbit of a satellite with just hearing it, which is really interesting. There are a lot of people working on that on the SatNOG team. And well, apparently Mehmet is also working on that, and they should talk to each other.
Okay.
Mehmet,
yes, thank you very much.
Screen.
Thank you very much for introduction. I'm directly starting my presentation in 10 minutes. It will be a little fast and maybe technical presentation. This study made in collaboration with some students and professors from the University of Turkish Aeronautical Association and published as a conference proceeding. Actually, after installing our SatNOX ground station, we asked why we don't use our own data to make an orbit determination. Then the study starts with aiming to make an orbit determination without having any information about the satellite. In other words, we just heard the satellite and wanted to determine it. Today I'm going to have an introduction about following stuffs. The details of the study will be presented as time allows. Lastly, I will show some preliminary results of the study. There are different orbit determination methods, as we all know, and different required data for them. These data are mainly optical-based or radio-based. In general, obtaining the data is in the control of some governments or militaries. There are also some commercial companies like Leo Labs. You can see one of their antennas in the right side. On the other hand, some civilian-based platforms also try to contribute space situational awareness. Actually, we do not have raw data in SatNOX. However, in principle, each station in the SatNOX can generate its own Doppler data. We also used a SatNOX station, as I said in the beginning. The UTA station generally seems offline, actually, due to a network problem at the university. I hope this will be solved in the coming weeks. However, we have a bunch of antennas there, and we used them in this study. The voice of the Sputnik means a lot for Geyer and Weifenbach. They discovered the potential of the Doppler effect to determine orbit of a satellite after hearing that voice. It was very beginning of the space era with launch of Sputnik in 1957. This table from their first paper, and they searched for orbits of Sputnik 1 and Explorer 1 in this paper. Actually, the story of their discovery is so interesting, but I do not give the details due to time limits. I may just suggest you to give a look at Gavagan's book, which is written in here. Doppler shift is a fundamental phenomenon for the waves, as we all know. It causes a shift on the transmitted frequency. That shift always decreases observed frequency during the pass, as you can see in here. You can see a frequency time graph of a satellite pass. Observed frequency is bigger than the transmitted frequency in the beginning of the pass, and it is decreasing during the pass. Also, the maximum elevation angle of the pass affects the shape of the graph, as you can see in here. In here, there's 20-degree maximum elevation pass, and 40 and 80-degree maximum elevation pass can be seen in this graph. In this page, you can see the flowchart of our study. First, obtaining a reference data is needed. That can be artificial or real data. We use artificial data to establish our method in a setting without observation errors. However, we also made some tests with real data. To obtain artificial data, we propagate the closest TLE and generate range rate data. That decreases our computation time, and that was needed for us. In real data case, we made a few observations, but signals have some incoherency, which will be discussed later. Also, obtaining data from the real observation is not easy for us. In the beginning, we tried to use STRF to get frequency time data. However, the given frequency of the STRF and the frequency on the screen of the STR sharp is different for the same time. We do not know the reason of that difference, so we decided to obtain data manually from the screen of STR sharp, and that was a hard process, so that affected our satellite selection criteria for the real data. After obtaining real or artificial data, we started the optimization process. First, boundaries and constraints should be defined. However, as I said in the beginning, there is an uninformed situation about the satellite. So we just assume a low Earth orbit satellite with 200 kilometers to 2000 kilometers altitude. That gives natural boundaries for 7 major axes to decrease search space. Also, circular and elliptical cases are searched separately. In here, we try to minimize RMS value, which is calculated with the reference raw dot and calculated raw dot during the pass. Then we start a genetic optimization to have preliminary results. In this study, particle swarm optimization PSO is used. The results of the PSO are not so accurate actually. However, They are accurate enough to be an initial condition of a gradient-based optimization. This two-phased optimization process gave a nice prediction about the orbit, especially if you thought there is no information about the orbit in the beginning. The results are fairly good for circular orbits. This process repeated 200 times and the best results taken from there. After that, we hope to improve our accuracy with differential correction. In here, we use Viados algorithm directly. It worked for some cases. I will talk about them. Finally, we hope to make some fine tunings on the process and having some more tests with actually real data in this year. After these improvements, we hope to have a repository for the work. Any kind of collaboration or comments will be great for us. This is the process of generating artificial data, as I mentioned. We use two-body propagator to simplify calculations and to reduce the computation time. These are constraints for the circular and elliptical cases. You may add a prograde or retrograde assumption if you want. This is not mandatory actually, because if you do not make an assumption in here, you can find plus or minus 90-degree difference between your result and correct one. That assumption does not affect the accuracy of the other results actually. And for the elliptic cases, we may increase our search space for the depending on the satellite, but for the low Earth case, these numbers are valid. This is the basic representation of the particle swarm optimization actually. Adding some mutation or other techniques to avoid local minimum points increases the accuracy of PSO. However, it may cause an increment for the computation time. And you can see the RMS calculation in here, as I stated before. The differential correction process is exactly the same with Viados book, as I stated, so that I will not talk about it. You can find algorithm in the book. This table is the results of the ISS with artificial data. The first line is our reference data. Then you can see the PSO results with absolute errors in the green lines. There's a 20-degree error at the most, but when we use differential correction for these results, blue lines appear and our accuracy increases to 3 degree for angular elements and 20 kilometers for semi-major axis. I think this improvement is really impressive for the differential, for the PSO, say. But more impressive results come from the gradient-based optimization. In here, accuracy of the angular elements increases roughly 1 degree accuracy. Also, accuracy of the semi-major axis becomes lower than 1 kilometer, as you can see in here. However, differential correction didn't work for that results. Most probably, we have an implementation error in our codes for the gradient results. If we can, for the application of the differential correction on the gradient results, if we can run it correctly, most likely results will be so accurate. This table is again the same results with the gradient-based optimization. You can see state vectors in here. In terms of magnitudes, 1 kilometer accuracy for position and 1 meter per second accuracy for velocity achieved. If you look deeper with 3 axes, the biggest error for position is in the Z direction, and its reason is the magnitude of the Z velocity. Actually, it's the biggest one, and the error is bigger in here actually. In this page, you can see results of 2 more satellites, which is NOAA 19 and Express MD2. The aim of this page actually is just showing that the increasing on the ellipticity of the orbit decreases the accuracy. However, we can start to calculate or predict the eccentricity with that way. And this is our test case for the real data. The Gurvin Texat 1B is selected because it was the only satellite which is periodically beeping for each 30 seconds on the observation day. We had also some other satellite signals with CV beacons. However, their frequency time data has some frequent oscillations. They just go like that, and we couldn't be sure actually. 2 minutes, okay. This is that This is another interesting graph for us. The blue line is the artificial data for GO32, which is propagated from the closest TLE. The red line is the observation data. There is a 2 kHz difference in the between the artificial and real data in the beginning of the pass. However, this difference decreases below to 1 kHz in the end of the pass. This is unexpected for us, and there might be some possibilities for that, but we do not know the exact reason. This variable difference has bad effects on our results. The yellow graph is our optimization graph, actually. You can see the Keplerian elements for this pass. The reason of the low RMS in here is having less data point. There should be 20 or 30 data points. Accuracy is not so good, as you can see, but enough to make a rough guess about orbit. Also, the most remarkable result is in inclination. It just dropped the lower bound of the optimization boundaries. All of these results show us that dealing with real data is not easy as artificial data. Finally, we see that usage of the gradient optimization with genetic optimization can give accurate results according to an uninformed situation about satellite. And also circularity of the orbit increases accuracy. As a future work, we need to try different propagation methods to improve accuracy. More tests with real data is needed, especially the process of obtaining Doppler data from an observation should be improved for us. Multi-station or multi-pass situation can be searched for the possibilities of more accurate results. Finally, after these improvements, we hope to start to preparing the repository. We are open for any collaboration during all of these processes. Lastly, these are the references of the study. And thank you for listening to me. I hope at least I can make a rough picture about the study. Any kind of question or comments will be great for us. In addition, you can contact me with my email address, which is written in the below. Lastly, I want to thank the organization committee to make this event online and give a chance to us to participate here.
Awesome. It's a very interesting concept, and it's really interesting because for us, I mean, during LEOP, the early phases after launch, we use the same tools like CRI and SAT tools to get the first TLEs of some objects, and for us it's very crucial and very important to have good TLEs and SATMEGs in order to allow for the community to get data. So we totally have to work together and figure out means and ways to collaborate further to see how we can optimize our data and stuff like that. And well, but you have some questions from the crowd. First and foremost, Fernando, how's the sender frequency is estimated?
Central frequency, actually, in this study, in the beginning of the study, we do not think optimization can find central frequency and give the central frequency to the optimization as a known quantity. And these results are in these results, the central frequency is known. But after the conference, we try to give the optimization process. We try to give central frequency to the optimization process, and we saw that central frequency can be found in the optimization process too. The error in the central frequency in plus minus 2 kilohertz or something like that, but the accuracy of the Keplerian elements didn't decrease with giving without knowing the central frequency. Actually, that was interesting, I think.
Mm-hmm. Oh. Fabian asks where he can find the orbit determination code that you presented. He's also online. He can ask it for himself.
Actually, you can contact with me. That we do not have any repository yet because the codes and process all of the processes are just in draft modes. But we can share all of the algorithm clearly. We do not have any repository for yet, because as I said, the project didn't finish yet. We hope in the future
Did
we
you
will
already decide on a license? May I ask a follow-up? Did you already decide on which license you will use for this? Because this is really important if you want to go public and call something open source. Then yeah.
Yeah, we didn't decide actually. Just our main focus is just doing it. Can we see? Can we find how can we be accurate? We want to see first that. Then we thought about the repository parts.
My personal suggestion, if you like to have it, is that release anything you got, even if you are not 100% sure it's optimized perfectly, because then the global community will work with it. For example, Elias, the person that's gonna speak after you, thinks that this optimization process might be really interesting, not only for subnodes, but for our upcoming satellite. So that would be extra cool if you do. Boris Agrev asked, is the intent to locate non-cooperative satellites independently? Like when TLEs are not by NOAA, I will remind Boris that TLEs are not provided by NOAA, they are provided right now by NORAD. Actually,
NORAD, I'm sorry. Okay.
18th Space Squadron, something. And what are the possible uses? Mehmet?
Actually, I missed some part of the question due to.
Okay, I try to tell it with other words. So this orbit determination is interesting from the ground for satellites when you don't have the TLE.
Yeah.
Okay, so what is the intent behind that? To locate satellites, unknown satellites, or to make some other uses of that? So what's the idea behind? And after, I'd like to comment on to complement on LF's suggestions just before. But what are the uses you have in mind?
I couldn't hear the last word actually. Sorry.
Okay, is my audio?
Yeah.
Is my audio correct, or do I need to?
Yeah, the audio is cool.
It's
okay.
about.
So why do you want to locate satellites?
Why do I locate satellites?
Yeah.
Actually, sorry, I couldn't understand the question correctly.
Okay. Well, I think the community can find some use for that.
I can first and foremost, I would like to point out that TLEs are not updated as often as it would be, because there are limits to the hardware, the hardware used by NORAD to generate them, and they have to generate them that often. And having verified theories of objects that are in orbit allows us to track them more efficiently. It's regularly done when we have a TLE that is publicly available. And Elias, that will speak right now, has some very interesting ideas that we will be tracking our future mission with the qubit screens.
Okay, just a point about Eleftherios' suggestion that you publish your code is that you may find in the community alternative solutions. For instance, here your method seems to me, I'm not sure, seems to me based on an iterative estimator, but you could also have another approach like a model fitting approach. So there are multiple mathematical ways to address the same topics. So if you provide your code, then we can see what's the engine behind, and we can try other algorithms inside. Yeah.
Thank you very much.
Mehmet, thank you. We will get in touch. And now, well, my friend and colleague, Elias, has the mic. Elias?
Hi. Hi, everyone. Okay, let's get this thing working. Okay, so this presentation is it's more of a story about the whole cubic mission. I won't go into technical detail because actually this whole journey, I think, deserves at least 4 presentations of its own parts. So we'll get a more of an overview of what happened and how it all started. So, not this August, 1 year ago, we got like an offer to have a 1p pocket cube to go to space, and it was like, do you want this? And you have to get it ready quite fast. So it was mid-August, and we had to deliver a satellite by December. Of course, we were not starting from scratch. We looked to what subsystems we had ready or almost ready, and it turns out we had a comms, which was a project that we were already working for, Pocket Cube comms, and that's about it, actually. There was nothing more. So we devised a plan. We would have to build the absolute bare minimum support hardware for this satellite to exist, make it all cubic, so it will become a pocket cube, while we would find an actual purpose and the mission objective for this hardware, so it won't be like just a beacon in space. And this was like the hardware and software plan that came into action. Now this is like the end of August. The idea about the experiment that could be performed with the hardware at hand is to attempt to make some RF transmissions that would allow us to determine the orbit and actually produce TLEs from the very early stages of the deployment, like within the, I don't know, first hour or something. To do that, we would try to exploit several aspects of the beacons transmitted by the Pocket Cube. Of course, there's the Doppler shift that the previous talk was about, and we're going to exploit that, as well as, of course, decoding the data and detect which satellite is which, as well as trying to determine by the beacon interval or the preamble and postamble length of the transmission, and stuff like this. You can actually read the detailed description of the whole aspect of the presentation in of the mission in this link. Meanwhile, on the hardware, there were stuff that needed to be built in quite a fast pace. So there was an initial power budget, and this called for solar panels, which were built up around the proven SPV 1040, and then we added an extra like power management chip that would monitor the battery and deduce the capacity and the available charge, etc. And this was built around the Max 17261 from Maxim. Also, the comms board would need a bit of modification because it was never actually fitted to a full structure, so the antenna connector needed a bit of a reorientation and also some minor changes so it would communicate with power management hardware. And in parallel, there needed to be like a structural design that would fulfill the requirements for a satellite to go through all the tests and then a release mechanism. And of course, all this had to be within the specs that the deployer that it was gonna be into would accommodate it properly. So to optimize the whole process, we actually came up with a design that uses the PCBs as a structural element. On the left side, you can see an exploded view of the whole satellite. And if you look closely, you can see that these are the subsystems that are all connected all together with spacers and these long bolts. And for the actual rigidity of the structure, the PV panels snap into each other, like in the picture on the right, and this forms a very rigid structure. This is a view of the antenna deployment mechanism. This uses the classic thermal knife approach, which is, I would say, a glorified resistor of incorrect wattage to produce enough heat to melt this tiny wire that holds the antenna in place. We have to do lots of tests about this mechanism. I'm sharing a slow motion mesmerizing video about for a deployment. So we had to do lots of tests to make sure that every possible scenario that this mechanism could fail actually be mitigated. And after many tests in a vacuum chamber, we came out with the value of 12. That's 12 ohms that this resistor should be there in parallel, and both of them can release the antenna. And then we get some news that we can actually, instead of one, send 2 satellites, which is great because they would be really, I would say, almost identical in the transmissions that they would be making. And this would make the experiment harder, but more valuable on the fact that now if we could actually distinguish between the 2 of them, this would be a great milestone. But there was some extra information about the deployer, and the extra info about the deployer was that it's more of a concept than an actual, device. And we ended up building also the deployer for the mission. So there was a new plan, which included building a deployer from scratch. And there was actually a point where we were required to provide a mass simulator of what the deployer is in respect of the center of mass and we had to do that without the deployer being being in existence. We did that to our best effort, and then in parallel we also built the deployer. Luckily, the mass simulator and the deployer were within the tolerances that were acceptable by the launch provider. And this was the birth of the Picobus. So that's the deployer we built in a nice C3PO gold color. It can house up to 8 1P pocket cubes into rails, use constant force springs to eject everything out, and utilizes thermal knives also to release like the door mechanism. And this worked actually quite good, and I think there are plans for this to be an actual service by LibreSpace. Of course, this had to go through vibration and thermal campaigns, which happened in Madrid and Barcelona. And back to the lab, the PCBs were getting ready for the satellite to be built. You can see on the right, this is an inspection of the conformal coating that was applied to all the circuits. And here is like a better view of how the whole structure comes together. So as you can see, there are like these small frames that help hold the 4 sides of the satellite in place, and all this provides a really rigid structure. And actually, there was a spare slot on the subsystems, which would have to be populated by a PCB. And since there was no subsystem that was readily available to go there, we send the LibreSpace Foundation manifesto etched in a PCB. You can see on the right there. These are the 2 pocket cubes fully assembled inside the clean box, ready to be integrated. Of course, they had to go through protoflight campaign. So the newly built deployer with the cubic mission, as long as, and also the rest of the, let's say, passengers, went again for vibration testing as the protoflight campaign. And then there is the software side. Luckily, there was a bit of extra time, so we moved on from just the bare telemetry that would be needed for the experiment. And the software evolved quite a lot, actually, because we have a fully functional driver for the transceiver chip. We implemented telecommand also. There is a finite state machine that controls everything. There's a new project that emerged called Open Space Data Link Protocol that implements some CCSDS specifications for the communication. And also there is ground station software for controlling the satellite. In addition, the development was done while being already integrated to the SatNOG's network. So while we were doing software testing and the satellite itself was transmitting the telemetry, and there was a SatNOG station next to it, and it was receiving all the telemetry data that we will be getting once the satellite is in orbit. So we're more than ready on that part, and that's, I think, quite new for this type of missions. Finally, there was the integration. This is the final charge of the batteries before everything goes into the deployer and it's sealed to be shipped to the launch provider. And on the right-hand side, this is the clean box where the whole integration happened. There's actually a full-length integration video on the LibreSpace channel if one would like to watch it. And a few things about the launch itself. The launch was part of the Dream payload provided by Firefly Aerospace. It would be launched on Firefly Alpha. Everything was arranged by FOSSA Systems. And as it turns out, the Firefly Alpha rocket, it will be actually its first launch. So lots of unbuilt and stuff being here, but so far it worked okay. We really hope that Firefly will not become a fireball. And the launch should happen, I think, early next year. I would like to thank the whole Cubic team and the people that helped for this mission to become a reality. We would like to thank FOSSA Systems for arranging also for the facilities for the thermal vacuum and vibration testing. And we're at the state now that we just wait for the launch to happen, and we can finally have some pizza. Thank you very much.
About time to have some pizza. Awesome. So I have some comments, not questions yet. Actually, there are some mentions about the message we sent on the LibreSpace manifesto values. Spanner Voyager style message for outer space. Yeah, but it won't last that much, that long. Actually, cool piece to give away. I have that noted, and others of us, I'm sure that they would like to get their hands on that. Me too. I want that on my keys, man. Oh, yes. Karel is the repository that you people can check it out. And yeah, I'm checking out any other questions that there might be. I don't see any questions yet. Yeah, I see Agis that's really excited about your presentation in YouTube. So, I suggest no.
So I would like to say that Jan said that's a very cool piece to give away. Maybe it's a good idea to have some boards printed and give them or give them away or sell them for I don't know, to have some income for the next mission.
We need to sell a lot. Oh, Red has the awesomest co-presenter, but he can't hear us. He's waiting for us to go to room 1. So, stay awesome. Great talk, Elias. And catch you soon.
Bye.
Bye.
Let's go to room 1. Go out. I'm gonna shut the lights off, so I'm closing the air condition. So the workshop continues in 10 minutes in room 1. So just this. Oh, I see you in 10 minutes in the other.
Artur is still on mute. Okay. So apparently, some of you might already know Artur. He's an electrical engineer, an OSCW volunteer extraordinaire. He's actually gonna do an informal workshop. It will be around an hour or less. And it will be about storing large data and visualizing it with as simple as possible approach, which is well, quite interesting. So, Artur, you got the mic and controls.
Thank you, Elkos. And hello, everyone. So, okay, I guess we're complete. So I'll give a short introduction about what this is all about, very briefly, and then we go into live coding. I was about to write what you need for this coding, but actually you don't need anything, just a web browser. It's going to be all online. Let me see, there was something on the Riot chat. You're not invited. Okay, that's not related to here. Good. Well, I really look forward to you following along with coding. But let's first give you a short introduction about what this is all about. So the onset is that when you do mission operations, or in fact any kind of other activity, like controlling drones or rovers or household automation, you need to store data, and then the next step would be you want to visualize the data. And that would be a typical dashboard that you would expect. You can see here you have a map, and we have some time series data here, some metrics. You can put this as a plot, or you can have this as a table. Yeah, and the question is, well, I tackle these two questions. First is, how can you store the data? And the other question is, how can you then plot this data? By the way, on this dashboard and on many other dashboards that I've looked, I don't see a kind of schedule view, meaning that in particular for mission operations, you deal a lot with schedules, for example, with ground station contact times to a satellite, or with shifts, or with procedures that run. That these are things that have a start time and an end time, and you could visualize those as a Gantt chart. But actually, there's no library, or maybe I haven't found it yet, that makes this easy to plot this in the web browser. So I created my own. Well, but of course, before you start writing something, it's always a good idea to look at what's already available in the open source world. And some of these projects maybe are very good, but then they're so small that it's really hard to find them. Others are really big. They might be also very good, and they're well known for their purpose. But for me, like one of the first things I looked into was this Elasticsearch. There's also a front end called Kibana to this. But the experience for me was I do a put, so I input some data, a movie here, title, direct, and a year. And then in the next step, I want to read out to see what I have actually inserted. And what I get is this thing here. So a lot of meta information and stuff that, well, I was not interested in. I just wanted to basically get this thing back. Could be that I'm just a fool and I don't know really how to operate Elasticsearch, and I also found it a pain to set it up. But yeah, this is where it started to develop the idea that I need something that is more simple. And the reason for that is I'm a simple man. I like to have things simple. Yeah, and that's why I started this endeavor. And then we go directly to the live coding part. So I mentioned that I like this things to be simple, the tools, and I also like them to be abstract of technology. So what you will see now, I'm actually using in the background or as a backend, I'm using MongoDB and Timescale DB. But if you're using my libraries here, that's totally transparent to you, and you will see why. So I'm going to share my screen. Okay, let's stop my webcam. All right. So the live coding will work like this, that I prepared a Jupyter notebook, actually 4 of them, and you will load them and you will code with me together through the notebooks. And this is really cool. There's this binder project. So you see here, I have this GitLab repository where I've prepared the notebooks. I tested them locally. Everything is working. And then I go to this. Well, first of all, I send you the link here in the chat. And then you go to mybinder.org. Well, actually, you don't have to go there because I'm preparing this for you now. The important thing is that you select here GitLab, and then you paste here the link to your repository. Well, you have to select the repository you're using. Of course, everyone is using GitLab because it's not owned by Microsoft. And then you get here an URL to your binder environment. So you copy this URL. I copy it here for you in the link. And then you open this. And what will happen, and it will take a bit, but it's really cool. It's going to create now a virtual environment for you. So it's preparing for you, for me, for everyone who's using the link, a dedicated environment where you can run your notebooks without destroying. And you can even change the notebooks. You can rewrite stuff. But take note that this is when you close it, then all of the thing is of course lost because it's just running in a virtual environment. And this makes it then really easy and nice to share with others during an online tutorial, for example. You can also see what's happening. So it seems like there's really a lot of people following the tutorial now because it took a bit of time. Okay. Let's make this a bit bigger. You should hopefully also be at this stage now that you see these 4 notebooks. There's also a requirements.txt file that shows you what other libraries or what libraries I have used to install this. Of course, you can also download this repository and run these notebooks locally, but then you have to make sure that you install those requirements via pip install -r requirements.txt. Good. Can you please shout out here shortly if you are there or if there's a problem? Shout out if there's a problem.
Oh, we're there.
Okay. So then go into the first one, the document store. All right. So the idea was that if you want to store data that that you don't know the structure beforehand, I mean, most of us are familiar with SQL data, MySQL or MariaDB. You define your schema, so basically your table layout, what kind of information you want to store there, and then you insert data. But many times, like if you think about JSON or Python dictionaries, many times you might not know in advance how your data structure looks like, or maybe your data is even diverse. Then a NoSQL database is likely better suited for that. And as I told you, in the background, I'm using MongoDB, but actually you can replace this with anything else that fulfills this pattern. And the pattern is as such. I'm storing data using a domain model category approach. So that means it's also a REST API interface that you're dealing with. So that's why it's technology agnostic. So it's running MongoDB, but you're interfacing it via REST API. So in the end, you don't know actually what database is used in the background. And what you do is you do requests to this URL and / a domain / a model. So you can think of domain would be your project or a mission or some domain of interest that you're working on. And then in this my model, you would capture different aspects of this domain. For example, eclipses or parameters or temperature and so on. So for the rest of this tutorial, we assume now that we are going to store the contact times between ground stations and satellites, such as you would likely need for SatNox or, well, basically for scheduling passes to ground stations. Now, if you want to run, if you want to set up the document store locally, then you would follow these steps here. So let's just zoom out. Basically, you clone this repository and then you Docker compose it up. And that's what I'm going to do now. So you don't have to do this now, but of course, you can do that. But for this tutorial, you don't need to do that because I have set up one on a server. So I go into this repository. It's just a few files. If you actually look at the Docker compose file, I mean, it's fairly simple. Really just, it's quite easy to understand what's being done here. And there's one caveat or one different thing, one change that I had to do is I had to set the port to 80 because for whatever reason I cannot access my this virtual server over a different port, only over port 80. So that's the main difference, but yeah, I don't know why it's like this. That's only for this virtual server that I rented. So Docker compose up. And by the way, I did not pre-prepare it, so you can see it's being built live. So it's pulling the repositories, this Docker image, extracting it, and then building the thing. In the meanwhile, this shouldn't take long. But in the meanwhile, you can look here at the imports step 2. So if you run it locally, you would use this step, and then this port also works fine. But we run it for this tutorial using this demo server. And I say it's on port 80, so we don't need to specify a port here. Now, important, please listen. That's important now. Because we're all working on the same server and putting data there, it makes very much sense that you use your own domain so that we don't clutter each other's data. So your name, replace it with your name or anything that hopefully is unique among us. So that could be the name. Is there another Arthur? No. Good. So that should be unique enough. So you have to set this domain. And then the rest is fine. And now we execute the cell. And to execute a cell, you hold the Shift key and press Enter. And then you see here your URL. And this part here should be different for you. OK. Just to double check that our server is up, we take, you open this one in your web browser. Okay. Yeah, sorry, this is my cache. I don't know how to overcome this. I have to, it auto-directs to HTTPS, but it's not HTTPS, it's HTTP. Wow, so I tested this literally before. Okay, anyway, so here it is. Right, so this thing is up. Seems like somebody already tried it. Okay, so we are here at step 1. Everyone can read, can access the server. Now we're going to enter our first data. So we do this by doing a post. And our data is a dictionary. So it's a satellite and a ground station. And so we schedule a path for the satellite over this ground station. And this is the start time. That's the end time. Note I'm using here this ISO format, also with the milliseconds. You don't need to do that. But it's generally, you see, if you can also do it like this, but then you have a space in the syntax, and better not. Because later you do queries also via the browser, and it's good if you can avoid this space here, so to be consistent. So insert the data, response 201, so that was successful. And actually, let's have a look here at the server. Ah, damn it, I need to go to this incognito mode. HTTP, yeah. See, I can see already a few people. Too few people, please. More people. You can see domains are being created. Yeah. Okay. One, two. So I have 2 people correctly following and another one not quite correctly following, but still following, and myself here. By the way, can you see that? So this admin config and local, this is just the MongoDB thing. Maybe I would filter this out at some point. But you can see this domain's created here. Good. Next, I'm inserting more data. See, I did insert a dictionary. If you want to insert more data in one go, then you use a list of dictionaries. And yeah, I post it to my endpoint. And yeah, I can do a request to see actually how my endpoint looks. It's easier to do this in the browser because then you can see it's more nicely formatted. So in my case, that was my domain, and that was the model name. So you would see that those entries are there. They all get this unique ID. That is actually something that MongoDB is doing, but we keep it because it helps to identify these individual documents. So you have all the data there. And they're all more or less similar structure. You have satellite, ground station, start and end time. Now I add yet another path, and this time I add a node. And see, and this is NoSQL. You can just open another field, and it will work. You can see this also here. And by the way, I request here the data, and I do a formatted as a data frame, so it's more pleasant to the eye. Maybe I should filter out this ID field because it doesn't add much value. But you can see that this last entry we did created a node. It had a node field, and that's not a number or not a value for all the others because we didn't define it. So for pandas, it looks like that's not a number. But if you look on the web, you see that these are just the listings of the entries as you did. And then this dictionary has this additional entry of the node. Okay, so far so good. Now, next is we know now how to create entries and to do a bulk insert of entries. And we know now that we don't have to structure them in the same way. In fact, the fields can be totally arbitrary. So that's the key of a document store. You basically store dictionaries there. Let's replace one entry. So for this, we need to specify the document that we want to operate on. Replace. So to replace an existing document, let's replace this first entry. So we copy the ID, copy it over here. And we replace this whole entry here with just hello world. Do this. Yeah, let's see the result. And right, see? The first entry was completely changed, and all these values now are not there, and only hello world is there. You can see this also here. Just hello world. Fantastic. Next is if you want to modify an existing, not replace a document, but modify it. So let's go up a bit. We have this one here, node. This path may be cancelled. So we got a confirmation it's not going to be cancelled. It's going to take place. Copy the ID, paste it here. And we're going to change this node so that it's confirmed. Okay. Let's have a look at the effect. I just go up again and list it here now. And you can see this path is confirmed. So the node was updated, this particular field, as we wanted. By the way, I'm not I don't read the chat. I'm focusing on the notebook. So if you have a question, open your mic and ask me live, please.
Juan asks, Juan Rojas, why change the column name?
The column name, which one, where?
The first row, actually, I'm sorry. The first row now is hello.
Because this was the insert of data. No, sorry. I replaced the whole document. That means basically you have this ID endpoint. This stays as is, but everything else will be replaced. And I just put this document here. That means it has no value for N, ground station, satellite, start, and node. So this is all gone. And instead it has a field called hello, and the entry is world. So,
okay, I get it. Now you created a new one.
Basically, you're overwriting what was there. Okay. So this was inserting data, replacing data, modifying data. Let's go to the read section. We already did a lot of reading in between to see the effects. But let's start formally to get a list of all the domains that you have on your server. And you just do a GET request on the host URL. You can see the people who are actually following. Then let's get a list of the models in your domain. You see, I'm just doing just put host plus the domain, and we have only created this passes model yet. And if I want to get a specific document, I can do as well, but then I need to get an ID. Let's copy this one here. And that would be modify patch. Let me just confirm. I take this one here. This one I copied, right? Okay. So anyway, so I can get the values of a single document. Most of the time you might not, if you want to see, and then if you want to see all the data stored, you just do a GET request on the endpoint. I must say it's quite uncommon actually that you work on documents via ID. There might be use cases, but and also you don't usually get the whole, want to work with the whole data set because it should become quite large, and I'm talking about millions of rows or sorry, documents. So what you then need is filtering, and I already mentioned that NoSQL leaves you the it doesn't predefine a schema that you have to use, and that's great on the one hand because you can arbitrarily then define new formats for the documents fields. But it's when you retrieve the data that you have to put extra attention because you have to know what you're looking for and you know to know what you can filter for. So the endpoint is this one here, your domain and the paths that we created so far, right? And what I'm going to do now is to filter for specific fields. You see, you have the ground station field, and I want to filter for those ground stations that use, or the ground stations called antenna X and antenna Y. So I can, this is this special operator to denote that the following thing is a query, and then you write the field name, and then equals to, you can specify one value or several values via a comma. And you can see in the reply, we get antenna X and antenna Y results, and there's actually only 2 of them, right? The other ones are antenna Z. You can also filter for more than one field, and it's an AND concatenation. So meaning now I'm looking for antenna X and those that are allocated to satellite X and satellite Z. And there's actually only one. So antenna X is tracking satellite X, but it's not tracking satellite Z in this case. Well, you can play around with this by inserting much more data, and then you can see how this filtering works and also how fast it is. So I say you can filter for specific values of these fields, but you can also, and that's really the powerful part, you can apply some filtering logic, operators. I list them here. So you can have lower than, lower or equal, greater than, not in, so you can exclude values, field values, and so on. Also regular expression. So for example, if you want to, let's say, have all the passes that start from March onwards, let's say, that's 2020, but you can see this is all from 2020, and I want to have the values that start, the passes starting from March, and you can see them here, and those are the April passes. And again, you always see here the URL that is being formed. Because in fact, if you go over and use a REST client or even just your browser, then you will get the results here as well, right? So your browser it's basically a REST client in that sense, and you can see that. That's also the reason why I prefer to use this ISO format, because then you don't have this space here in between, and the space sometimes this gets converted to this weird symbol. So if I leave space, I think it would work. Yeah, but I prefer not to have a space in the URL. Okay. We were here. Then this was filtering. That was the big thing, filtering. You will do filtering a lot because you need to find the documents of interest, and so you need to filter for them. And then you get data back, and sometimes you get even when you apply filtering, you still might get a lot of data back, documents back. So you want to, one way to handle this is to do pagination, meaning that you say, okay, give me back results in chunks of 2. So 2 documents per request, or let's say take all the data, all the results, and yeah, put them into chunks of 2, and then give me the chunk or the page number 2. And then you get here these 2 replies, and this would be basically the second page. You can compare this if you know 1, 2, and then you will start here 1, 2. Another nice feature is, of course, to just apply limiting. So you can say I don't even apply any filter here. So I request everything, but I limit it just to one answer, to one return. And the cool thing is that this is being done on the server side, of course. So it's not that all the data is being sent to the client and then it will just display 1. No, it will only from the server send 1 or 10 or whatever limit you specify here. And this is quite handy if you want to, for example, get your latest entry. Then you go from that comes later. You would sort it by time and then limit it by 1. And then you get your latest or your earliest entry, etc. Quickly, projection is, as you see, you always get the full result here. Everything that you put in the documents, you get returned. But sometimes you maybe just want to see, let's say, the satellite and the ground stations involved in your data, and then you filter for the fields. You might have also noticed, hopefully, that all these special operators, they start with the underscore. So whenever you don't use underscore, it's interpreted as a field, and then it applies this filtering onto the fields. But if you use the underscore, then for the sorting, for the limit, and so on, then it knows this is a special operation, and it will apply that. So in this case, I get only the ground station and satellite fields back, and the ID is always there. So that's just an artifact. We keep it for now. Sorting as well. You can specify the sort. Again, it's a special operation, so underscore. And you say, I want to sort by satellite, but in reverse direction. And then in the second, so that would be the first sorting priority. And then the next would be to sort by ground station. Again, I show this one in the browser. Make it more clear. So we see it's sorted by antenna in reverse. So Z. Okay. Sorry. We sort first by satellite in reverse. Z, Y, X, X, X. And then the second is by ground station. So Z, Y, and here's X, X, X. So X, Y, Z. Okay. So satellite is ordered in reverse, but then within the same satellite, the ground station is ordered alphabetically. So yeah, all the things you need to filter your data and to sort it. Good. Next thing would be, to sort. So this was sorting by some fields, but most of the time you probably want to sort by time. And for example, to sort by start time, you would do like this, and then you get all your passes ordered by start time. So, this one is the next pass taking place, and then the start time is here. What did I do wrong here? No. Start time. Yeah, to February, April. So good. So we have a lot of data, but at some point you want to delete the data or clean up. So you can specify a specific ID. Clean that one. Done. If you want to delete more than one, you can apply a filter. So, example, I delete all the ground stations that that are allocated to antenna X and Y. Boom, gone. 2 are deleted. Have a look. So we have only Z here, and then this entry here left over. And then we can also delete the whole domain by just hitting a delete request on passes model. So it's a HTTP delete request on the passes model. I could also, and I can also delete the entire domain. Yeah, by doing a delete on the domain. Actually, since the passes model was already the last one, I will get an error here because, and that's a nice thing. If you delete the last, yeah, if you delete the last model in your domain, then your domain also has disappeared because there's no data in it. Here's some information on when you have your data. If you want to dump it, there's also utility functions to dump the data into JSON format, and that makes it easy then to share it with others rather than having to do copying it directly from the MongoDB database. Because I repeat, we want to be agnostic of the actual backend storage. Wow! So this is part 1 of the tutorial. There's 3 more to come. How do you feel so far? Can I get some feedback?
Awesome.
Hey, very interesting.
Okay, that keeps me going. Let's close this. So yeah, so this is via the I use this request library because it's much more human friendly as compared to this URL lib from Python. But still, what you were doing is to create basically text strings and then passing this to the requests module to execute it. So basically, you were doing the same as if you write this expression here in the browser. So that's not very Pythonic, I think. That's why I wrote this RESTDB client, which then provides a Python interface to this REST client, which seems then a bit of overhead. But the whole idea is that you make this thing, this database available to, well, basically any language you're using, because you have this REST API interface. And then it's convenient to have, a local client in your language to make dealing with this REST API easier and more idiomatic, I think is the word for that. So let's get started. You would install this if you do this locally. Again, here you need to make a change here. We're going to use this demo server, right? And again, put your name. And now everyone can follow because this is really short and easy. So please put your name here and let's go. So I'm not using the data from before. I'm using another data. And that's how your REST client should look like. You're connected to this server. And we're now defining a bit the solar system here. So you can see that I have this client that is connected to this URL, to this host. And my domain is here, my name. And I make an object that way. And so this is my domain object. And within this domain, I create a model called solar system. Okay. Boom. And now I have a data set is a list of dictionaries. I write here planets, their moons, and sometimes I leave out this information. And you see it's totally, they do not look the same, right? I mean, the structure here. The content, of course, also not. And then I use this insert method from the model to insert this data set. And you can see here that's all Python. It's a dictionary, list of dictionary. I use a method. I inserted these 3 data sets. In order to read the data, I do a find request, or I use the find method. And here I would then could provide a filter. But if I don't provide a filter, then it will just return me everything. And in order to make this look a bit more pretty here on this screen, I use this JSON dumps for this. But basically, yeah, just your data is in the data sets, and here I'm printing it nicely. So it's not so nice, but at least it's better, easier to read than without this one. So the data is there, and everything has their own ID. Okay. And as a next step, I'm applying some filtering. So in this case, I want to get all the planets that have moons that have more greater equal 1. So that have at least 1 moon, or as specified here. Right. So I didn't put anything for Mars. So even though it has 1, but in this data set it doesn't. And I'm here with Earth and Jupiter. And in order to delete, so that's how filtering works. I don't go through all the other things because it's similar to this, to what I showed you before. But you work here with dictionaries. So that's the nice difference, that you can be more Pythonic here in defining your filter and or sorting and fields. Okay. And for deleting, I can also apply a filter. So here, this one will delete the Jupiter entry. Okay, see, it's gone. And you can, meantime, you can also go to the to your browser and just verify that. See, we have 2 entries left. And then the deletion and of models and domains and specific entries, this works then the same way as before. So you have this model and domain objects that you create early on, like here. But even that, sometimes you don't want to do it. It's a bit maybe too cumbersome to write. So there's also some helper functions, like if you just want to load data sets and you know the name of the domain and the model, then you can use this helper function. You provide this client object, and then here this is text, right? That's the name of your domain, and this is the model name, and you can supply filters and so on, and then you get the results as well. And that makes it more, easier than to automate this thing. All right. Okay. That was the fast one on this client. And close this one. Now we go to the, so this was all about documents, storing kind of the dictionary-like data. Now let's talk about time series, because this is the other kind of data you see a lot in, let's say, in the Internet of Things or your metrics of your computer. It's the characteristic of this data is that you have a timestamp and a value, and all the other things you cannot. All the other metrics you would have here, you have to get out of the context, or you have to log it in a different way. I think right now I'm not sure if you can even store more fields. But here it's the same approach. You have a domain and parameter category. In this case, I call it not model, but parameter. That's more or less the same way. So you provide your URL and access it. For example, your device, your Raspberry Pi that you use at home to measure the room temperature, that would be your device. And then the measurement it is taking here, the temperature or the current or the voltage or whatever. And then you would put your values here with a timestamp and with a value. And for this tutorial, we assume storage of temperature measurements of a satellite. Again, we're going to set up now the this time series store. Oh, I lost my connection here. This one here. I have to close it down because, as I say, it's only with the server. I have to run this on port 80, and there can only be one on this port 80. So at home, you can have them running, of course, in parallel, and you can define which ports they run on. And again, it's building now. So once this thing is built, so you build it once and then you run it. But this is like out of the box, completely fresh, just waking up. And there's one feature that is also explained in the README. Is that when you've started for the first time, you have to stop it again and start again, because it's setting up something, and for this you need to restart it. I'm sure there's a way to handle this. I don't know how to do it. So if you find out how to make this nicer, but it's really a minor thing. Once this building is done, you stop it and restart it. Meanwhile, same thing here. We're not running it locally this time, so we're using the server that's already prepared for you. Put your name again here. Small letters. And we're storing temperature Y data. Don't execute it yet. But actually, you can execute this part. And then you should see a URL like this. And it's not ready yet. You see, it failed. So I just stop it here and I start again. And this is also how fast it would take usually to start up. You see, it's a second it took to start up. So once this thing is built, it starts up super fast. Let's have a look. It's not, there's no data yet there, but you can see, well, there's no data in it yet, but the server's up. You can test this now that you can reach the server. Let's put some data in. And I just warn you that this request will not work. I'll tell you also why. So execute step 3. We want to insert data with a timestamp and a value. And we get a 404 response. And this is because, well, in the background, this one is using a SQL database. It's a Postgres. And actually, it's this timescale DB, which works on top of Postgres to make this really able to store huge amounts of data. And in this case, you need to define beforehand what kind of data you're storing. And we do this now. So we write to this meta URL or endpoint. We define, first of all, the name of our domain, the name of the parameter, and the type. And here you can, you have to look it up what types you have available, but those basic types like float, int, string, and so on. And this you do only once per parameter that you want to store. right? So we do this now. So it's created. And actually, let me test if you can see this here. If I created this endpoint. Yeah, right. So you can see here all the domains, model, parameters, and types. So each of these 3 people here, they have created one. You have to create separately per domain because domains are completely separate from each other. That makes it possible that many users use the same server. And now we repeat what we did before. We want to insert data. And well, seems like it worked this time. 201 means something was created. Before we have a look, let's add some more data. In this case, it's a list of dictionaries. Okay, and now let's have a quick look if we actually, let's have a look at our server from here. So we look at all the domains that are on the server, those 3. Let's get a list of all the parameters we defined in our domain. Temperature Y, only 1. And let's get all the data from this endpoint. Whoops. Did I forget? There's a typo. No. Okay. Who spots the typo? Interesting. That's the endpoint. Temperature Y. Posting to it. And I don't get anything. Ah, that's not good. Let's print it.
So I also got the non-empty result, the same as Juan, but I'm not sure why, Arthur, you don't get a result.
So you have the data.
Yes, and Juan also.
Okay. Maybe the name. Can you look?
I will try with your name also, man.
Yeah, if I search your name, I don't have any data.
Okay, so maybe I have a very special name and this is protected by timescale DB or whatever. Okay, that's something to look into. But if I look at your data, I see it here. Very good. And let's then let's rename our endpoint. I make this. Good. I hope you're okay if I use your data now. So I say that the domains are separate, but nothing keeps you from using the other people's data. So let's do some filtering here. Well, it's not filtering. It's you specify a specific time. You want to get the value of this, and you see I have exactly. I get this entry here back. You can also supply comma-separated several dates, and then you get the entries for those dates. Maybe I did a typo here also. Yeah, there's no. Take this one here, 15. Well, anyway, you get the meaning. So I can provide a list of timestamps and then I get the values. But again, nobody's going to do that. Most of the time you use just some filtering, like everything that's from January 2nd onwards. Okay, so there's none, of course. Let's grab 1st of January, let's say 10:15. And we have greater or equal, so that should be included as well. See, 10:15, 10:20 entry. Again, limiting to 1. Just get 1 result out of all this, and then I can sort by time, minus time even, so get the latest one. Oh, sorry. Now it's sorted backwards in time, and then I can limit it, and then I get my latest entry. That would be that one here. Okay, so more or less the same approach like with the document store, but this time for time series data. Now, the next step would be to delete data, and that's not yet implemented. You might wonder, oh my God, why not? It should be fairly easy, but it's not, because you remember we define this metadata here to tell the database what data we have, and we still need to think about, are we going to delete this as well? And so yeah, it's still ongoing discussion of how to handle this case. So you're very welcome to join us in this and make a decision here. Now comes the last step. I think we can finish this in 5 minutes. It's also good that we don't delete the data because we need it for now. We want to plot this data now, and this was actually should be, well, half of this, right? One is to store the data and retrieve the data, and the other big thing should be to visualize it. The tutorial now is a bit short here, but you can experiment at home with it. I think it's quite powerful, but still easy to use. So again, you don't need to install. We're using the server here. And here you put your name or the domain that you want to plot. And now comes the nice feature. So this Python data viz library, there's a lot of plotting stuff available, of course. Matplotlib, then there's Boki, then there's so many Plotly, there's so many plotting libraries available. But I was really inspired by this Vega Lite visualization grammar. That's for, I think, a JavaScript library. And they kind of abstract the definition of a plot from actually the technology to use to plot it. If you do a matplotlib figure, you know how cumbersome it can get to specify this and this and this and that. And then if you want to plot it, let's say with the pandas data frame library, then they use a different syntax again. So this Vega Lite abstracts it. Well, it suggests a way to abstract this data, but this is not available in the Python world yet, as far as I know. So I try to do it like this. So I create a specification, and this is not exactly Vega Lite syntax, but as close as one can get. And it's also not complete. There's still stuff to be done. But basically, you specify the layout of your plot. You specify where you get the data from, and how you want it to be drawn. And then you tell the fields that you get in this data. So we have, well, on your x-axis, you read the field, this time field, and you specify it's a temporal context. So it means it is a time value. And this one is a quantitative value on the y-axis, and you take it from this field value. You see, this library is not tied to this time series store. You can actually apply it to any URL. Actually, you can also pass in data frames. But anything that adheres to this format where you have time, where you have columns, data and columns, and this is basically for data frames or any kind of a lot of URLs that have REST APIs, like to plot timetables of buses and taxis and so on. Okay, so this is just a dictionary. And now we pass this dictionary to this data with figure creator. And then it, well, if you don't pass any parameter here and the time we want to display, then it displays the entire data available. You can also do some filtering here for some specific time. And we want to use matplotlib as a rendering engine. So if you execute this, so it seems like you created some more data. Oh yeah, great. So you added some more data in the meantime. And this is the plot of it. And you can see that since you choose very crazy values here, so you have 999 and 0, and they're all here. So the plot looks a bit funny, but basically it's plotting your data here, right? So it's all correct if you compare it with what is here in the database. But that's a matplotlib figure, so it's static. You can configure it. You can give some titles here. But if you want to get a more interactive visualization, then you can use Bokeh, which is very nice because you can zoom in. And then you would actually see that you have here data. I actually can zoom also on this axis. Well, let's reset the zoom. Let's make this. Okay. Yeah, you should really learn more about Bokeh. Go here, click this logo or search it up. It's really a cool library for this interactive plots. And you can see this is basically the data you specified here being plotted. And this is super nice to really inspecting your time series data or actually any kind of other data that you plot with this data with library. And this works also very nice as long as you're in the order of, let's say, 100,000 points. By the way, talking about points, they're called circle in. See, now they're drawn as small circles. We can zoom in. Again, this is Bokeh. So I'm just utilizing this really cool Bokeh library. But yeah, what I did is I provide a very easy interface to create those plots. And I say you can plot up to 100,000 points of data, and it still goes very smooth. But if you start plotting millions or more points, then this thing gets really laggy. And at some point, your memory will not be able to handle it, and then your browser page doesn't load. And there's another project called Data Shader, which is able to pre-render your data and then put this as an image. And this is really powerful stuff. And we're working on implementing this as well. So then you would have here Data Shader. It's not there yet. Yeah, exactly. So this is work in progress. And this is going to be even more exciting than to plot really large amounts of data. Okay, I have actually some more pictures on this, but yeah, I mean, I guess I stop for now. That's 1 hour of a tutorial. And I'm really happy to answer a couple of questions if you have before we make a break.
Questions, people?
Okay. Good. Anyways, you can redo this tutorial anytime. You have the links. You can download it, and you can contact me anytime with questions. Fabian, yeah, I think you have a question, right?
I just wanted to give it feedback because was just a bit overwhelmed to now find a good question. Sorry.
Okay. Good. I think then I thank you for your attention, and let's have a 10-minute break before we already come. Wait, my webcam. Before we already go to the closing session. So fast.
Well,
did you already? Oh, I have a question for Arthur. Maybe.
Okay.
Back to the topic from your tutorial. Do you already have a database where you put some actual satellite data into?
Actually, I use this at work, and as a support to do this, get an overview about the passes that we have. But maybe I think maybe Satnox or some tracking that would come to mind to be a perfect use case for this.
You think that would be useful for Satnox, Kerel, especially that you're better familiar than me with the project?
Yes.
Technically wise?
So technically wise, what you presented was really the nice interface with sorting and filtering, which is well, a good improvement over other services. From the implementation wise, we already have a database, so everything we can only use things which we can put in front of such a database. But I think the tools are there, and we could use the same interface to access or to modify it to write to use the same database we are using. This could be modified.
Yeah, from what I've seen, as far as some of it could be also be an inspiration, not only for Satnox, but for other projects or from something closer to the individual machines we have at home. See, you never know. We are much more hiking right now.
Well, let's say I'm using this. I'm using this myself a lot. So, and I didn't find any other thing that's easy to use and uses a REST API. So even if I'm the only user for it, I'm okay. But I think there's a huge use case. Just people maybe might not aware of this, so now they are. So feel free to use it.
Especially missions who want to work on their own data, doing manual analysis. Then you can also think about exporting a whole frame dumps from Satnox or other sources into such a database and then have a nice interface. And I think this is really a good tool for missions.
Good. Thanks very much.
Can you hear me?
Yeah. Juan,
so
yeah.
I was thinking about the integration with some kind of dashboard, something like that.
Yeah, we have, of course.
So that was super easy for you, but for me, I have no idea. So.
Well, the thing is, we also write a dashboard on ourselves. But you mean with something off the shelf, that not like Kibana also? I didn't try it yet. No.
Okay. Yeah, I was thinking something like that.
Good, but we can talk offline more about this. I have to leave now to prepare for the ending, which will take place in 10 minutes. So I look forward to see all of you in room number 1.
Bye, Arthur.
Good. Ciao, ciao.
Take a break. You deserve it.